So yes, the Eulerian trail is a trail, so each edge only once, that hits every edge. And a semi-Eulerian graph is a graph that contains a Eulerian trail. Doesn't have to, there can be trails that are not Eulerian, but and a connected graph will contain an Eulerian trail if and only if it has exactly two vertices with odd degree. You guys remember what degree of a vertex is?
The edges on a.
Uh-huh. They can be, but it won't have an Eulerian trail. So, is there an Eulerian trail here?
No, there aren't exactly two edges. There's just there none of them.
There's none. So that one doesn't. What about this one?
No, any of them.
Yeah, four of them have an odd degree. Yes. A and B. So let's see if we can figure it out. They don't necessarily give you this, they'd say find one. Yeah, that wasn't so hard. And how I would name that was probably AD, I'd probably name it by saying its edges. AD, DC, CA, AE, that I followed. Does everybody understand that? So if it asks you to find one on an exam or something, you're just going to name the edges. To determine whether, okay, yep. If the graph is semi-Eulerian, state one possible Eulerian trail, which we just did that. No, this is how they named it. They went A to E to D to A to C to B to E to C to D to B. So theirs goes like this not the same one I used. They did this to D to A to C to B to E to C to D to B. The key is though it'll start and end at one of those odd vertices. So you have to have at least two. The other ones have to be even because they have to have a path in and out. That's why that is. Your odd ones are a place to start and end. Exam tip, there it is. They always start and end at the odd degree. Important. An Eulerian circuit is a closed trail that contains all the edges within a graph. A graph that contains an Eulerian circuit is an Eulerian graph. A connected graph contains an Eulerian circuit if and only if every vertex has an even degree.
Wait, how was the circuit of the trail?
A, a circuit has to start and end at the same point, correct? Wait, is a trail hits every vertex once? Let's look at yesterday. Three. A trail is a walk that has no repeated edges. A path has no repeated vertices. A cycle walk begins and ends at the same vertex. A circuit is a graph that begins and ends at the same, is a trail, so it hits every edge. Connected graph contains a path from every vertex to every other vertex. What was the other term we needed? Trying to figure out how an Eulerian trail isn't also an Eulerian circuit, or how an Eulerian circuit isn't also an Eulerian trail.
Does it get started in the same point? No.
But doesn't a trail?
Oh, okay, so an Illyrian trail doesn't have to start and end at the same vertex, because it just has to be at a.
Yeah, so, but isn't a circuit also a trail? But it can't be because it says it can't be because this one, they don't meet the same condition. To be a trail that begins and ends at the same vertex. So, um, a connected graph. Maybe you can't be connected. No, both of them say a connected graph. At the beginning. So that would be an Eulerian circuit. So it feels like these are worded wrong. So it contains an Eulerian trail that is not an Eulerian circuit if it's too odd. Would be because an Eulerian circuit should be an Eulerian trail, correct? Because a circuit is a trail. I'm gonna go back and read those definitions again. Do you guys need this still on the screen? Yeah. Oops. This is where it gets a little tricky in some of these, knowing every definition. The hard part about graph theory is knowing every definition and every algorithm. Did you guys watch yesterday's? Okay.
Or it's often the
I was like, you're gonna need to watch yesterday's before you start because there's pieces of yesterday's that we're gonna use today. Okay. So, okay. Let me double check that. Okay, I'll double check and then I'll go back. A circuit is on a graph is a trail that begins and ends at the same vertex. A closed trail is the same thing as a circuit, is what it's saying. Okay.
Well, and right
What
below there,
would
it's circus.
closed trail, it would just mean the same thing as circ.
It's just another name. Well, it's Cognity's going, this is what we call it, but something a different book might call it a closed trail instead. That makes sense. Okay. It's like what Coleman's doing, there's two definitions of a derivative. You can use either one. Okay, this one definitely it has an Eulerian circuit. So I guess it did have an Eulerian trail. I'll draw it out. Yeah, that's how I make all your videos.
A very steady mouse.
No. Okay, the Chinese postman problem. So consider the graph above. I'm not going to tell you the problem until we work our way into it. Okay. Consider the graph above. Now each one has a weight. If a postman needs to travel each road to deliver the mail to all the houses along the road and wants to end up back at the depot, this is called the Chinese postman problem. The length of the walk as a weighted graph is the sum of the weighted edges in the walk. Okay, this is pretty easy. No matter how you do it, you end up back where you started, right? On this one. Because this one is a nice Eulerian circuit. However, most road combinations are not a nice Eulerian circuit. So this one, the length of a walk on the weighted graph is the sum of the weighted edges. That makes sense, right? We just add up all these. It says, determine the length of the shortest route the postman can travel. Really easy, just add them all up. All connected graphs contain an even number of vertices with an odd degree. Do you guys remember what connected is? Mm-hmm. Nice exam tip. You only need to know how to solve this problem for graphs containing up to 4 odd degrees for the exam. Okay, they're always even. So you need to be able to do it for 0, 2, or 4. 0 was really easy. We just did 0. Where, oh, we could just go around any of them because we'll have that Eulerian circuit. This one, well, this one we hit every edge too without any repeats, right? Determine the length of the shortest route. Degree A and B are 3, those are your odd degrees. The shortest path between A and B and vertex is along edges AC. It has length 7. So this one becomes a little more challenging. It's very easy to get every edge, right? But then if we started at A, we need to get back to A. That makes sense?
Yeah.
So my path went, I think I did this way, it doesn't matter. But I'd add up all the edges, right? Because that gets me there. And then I need to get back. So the shortest way back is 4 plus 3. That makes sense? So I do not, that's not an Eulerian circuit, but I can still make it back. I just have to repeat those roads. So here what they did in the problem, and it doesn't really matter which order you do them in because there they added up getting to B. Here they added up getting back to A. With two, it's really pretty easy. Because was it easy to find that path? I just kind of went around and, okay, well, what haven't I used? I just went down the next one every time I hit a vertex. Now, a similar process can be used when you have four vertices with odd degree, which is what we have here. All the corners have degree 3. However, you must connect two pairs of odd degree vertices rather than just one, as in example 4. To do this, you will need to analyze the three possible ways of grouping the four odd degree vertices into two pairs and then choose the combination of pairs that can be connected with the shortest path. So AC has a shortest path of 14. AB has a shortest path of 13. Do you see how I'm getting shortest path? Because 14 isn't the direct one, it goes through E. 13 is the direct one. BD is 15 for shortest path. CD is 12. So I think I want to start at C and end at D, and then I'll walk back through E. So options A, B, and C, D. No, maybe that doesn't work. So I have to group them together. A, B, and C, D, A, C, and B, D, and A, D, and B, C. Does that kind of make sense? A, B being 12, that's 25. AC and BD is 14 and 15. So I have to do both pairs. So the shortest, so if I do AC, I have to do AC and BD. If I do AB, I have to do AB and AC for shortest path. That's the trick to this algorithm. If I'm doing AB, I have to do these two shortest paths. That sums to 25. If I'm doing AC, I also have to do BD, which is 14 plus 15 is 29. If I'm doing CD, oh no, I already did that. What haven't I done? BC, 13 plus 16 is also 29. So I've got that. So I'm going to use that one. Does that make sense how I did that? So if I'm looking at pairs, this is AB. Okay, I'll get the colors to match. AB and CD. So I have to pair them. That's what the algorithm says. When I draw it on the graph, it'll probably become more apparent.
And why do we have to see?
That's one option. I have to check all of them. The other option, this one was A, C, and BD. And the third option was BC and AD. So I have to check all of the sets of possible pairs.
Why are those?
So those are the four vertices that are odd degree, correct? I have to check all combinations of distance from A to B and distance from C to D. There's no,
I need to. So, I- oh, okay. Do all of them?
we're trying to find the shortest path that he can take to hit every road and end up back at one of the vertices.
It matter that the paths aren't always connected though, like A, B, and C, D are connected to each other.
It's going to, yeah, they're not connected. That's part of it, and that's where the trick comes into this algorithm. Okay. Yes, A, B, and C, D are not connected. We're just looking at shortest path. As is the case with a lot of these algorithms, usually involve a little bit of a trick. So the trick then being, you're going to add up the shortest length of circuit is to add up I could think not do this. I think all the circuit lengths plus your extra 25. The sum of the weights of all the edges in the new graph. Choose the option with the lowest total and add the relevant edges to the graph.
So. You just act like you're drawing the circuit, right? And
Mhm.
just add 0.5.
Add 25.
Okay.
So, well, it's not even act like you're drawing a circuit. Add up every edge because you have to go down every road and then add
The shortest.
the smallest combination of these. Does that?
Does not make sense at all.
So the four edges are A, B, C, D. If I pick A, B, the shortest path from A to B is 13, correct? We're looking at that 13.
Yep.
The other two edges is CD. The shortest path from C to D is 12. It's not the direct path, it's through E. That makes sense on the shortest path.
Yeah. I don't
My
know.
next combination is I pick two edges, AC. If I pick AC, my other combination is BD. So I'm doing every possible combination. So I've done A with B, A with C, A with D. If I pick AB, my other one is CD. If I pick AC, my other one is BD.
Yeah.
If I pick AD, my other one is BC.
I just don't understand why the number comes up like 80 something, so why isn't the shortest block just 25?
Because that doesn't hit every row. So if I wanted to do this, and I don't necessarily know what it would be, but I'd probably go that. Let's just draw it on. Let's say I started A. So now I somehow have to get back over and do this road. So I'm going to take the shortest path from C to D. There's my adding the 12. Now I've hit every road. Now I got to get back. There's my 13. Does that make sense?
Ridiculous.
More than two edges with an odd degree, you're gonna have to go.
I'm
back.
going to have to repeat roads. And so this is the algorithm figuring
To
out
repeat.
the shortest path of repeat.
Okay.
And somebody has proven that it works. You're just going to accept the proof. Devin's like, yes, okay, I'll accept that. Does that make sense? And that's why, okay, I just drew it out. I had to try it. Can you guys see that pretty well in the green?
Yeah.
So yeah, that took care of our repeated paths for us, which was the trick that we needed. Okay. That's the Chinese postman problem. Not exactly easy, not that hard. You just have to know the algorithm. Okay. And I will give you, roughly a page front and back of notes for your next test to get all these algorithms and definitions for graph theory down.
When are the
Next Tuesday? Yeah, I know. I'm not looking forward to it either. I have to write it. This is where the traveling salesman problem goes in. You don't have to hit every road, but you have to hit every vertex. Okay?
Yes.
So a cycle, that's a path, I believe. Hits every vertex. Is a cycle that includes every vertex within a graph with no vertex included more than once. And this is going to lead us back to the traveling salesman problem, which is essentially how do you hit every town the easiest? Which you will have some where you have to go back through the same town.
Okay, so in a Hamiltonian cycle, you can repeat edges, but you can't repeat vertices. Yeah. And
You can't repeat edges without repeating vertices, so. But you don't necessarily have to include every edge. That's the difference between a path and a trail. Does that make sense? Okay, we got those down. So the number of different Hamiltonian cycles in a complete graph. What's a complete graph? Yeah, there's a path from every vertex to every other. Can be found by using the expression 1/2 n, number of vertices, minus 1, factorial. Factorial?
Like, I don't know if it's.
5 factorial is 5 times 4 times 3 times 2 times 1.
I guess just never had to like deal with.
You will when we get to stats. It's not hard though. Factorials, what you do with them isn't hard. And your calculator has a factorial button on it. I believe it's under probability. Be aware, while all complete graphs with at least 3 vertices have a Hamiltonian cycle, there is no definitive criterion to determine whether a general graph has a Hamiltonian cycle or not. So what's a complete graph? Everything connects directly, correct? There's an edge from each vertex to every other vertex. So if it's a complete graph with at least 3 vertices, there is a Hamiltonian cycle. If it isn't, we don't necessarily know. One rule that is sometimes helpful states that if all vertices in a graph of size n have degree at least n over 2, then the graph will contain at least one Hamiltonian cycle. So if you have a graph with 10 vertices, that would mean all the vertices have to have degree 5 or more. Probably. I'm gonna skip ahead because we're gonna run out of class time. So you guys are gonna have to go back and add these. Okay. I don't have time to wait for you to get them all in your notes. A Hamiltonian path is a path that contains all the vertices within a graph. A graph that contains a Hamiltonian path is called a semi-Hamiltonian graph. So, in the applet, 5 cities represent the vertices of a graph. The weight of each graph is the cost of traveling between the 2 cities within the edge. The salesman who is based in city A, that means it's where you have to start, must visit each of the 5 cities and return home. The salesman you ask to prepare the route for him with the cheapest, the salesman has asked you with the cheapest possible path. So, here we go. By selecting the edge at the top left, create a cycle A, B, C, D, E, A. What is the total cost? So that's 185, 121, 174, 199, 133. Okay. By experimenting with different selections, what is the cheapest? I kind of think it's A, C, B, D, E, A. I'm pretty sure. This is a very simple situation. In this activity above is known the traveling salesman problem. The nearest neighbor algorithm. Okay? So there's 2 different algorithms for this. And there isn't a great definitive solution to this. The nearest neighbor algorithm is pick a vertex of the graph as a starting point. The question will sometimes tell you to pick a vertex to begin with. If not, you can choose any. So that one told us A. Go from the current vertex to the nearest adjacent vertex that has not already been visited, which is what I actually just did. I did this algorithm without thinking about it because I've done it a few times and that was a pretty easy graph to do it on. So I went down the 119, that's the cheapest one. Then I'm at C. Repeat step 2 until all the vertices have been reached. So from step C, I went so this is the cheapest. Then I look at where's my cheapest. Oh, I did not do it. My cheapest is E. Now I go, the next cheapest is to go to D, I guess. Then I go to B. Then I go back. I believe that's nearest neighbor. Complete the cycle by traveling back to the starting point. That is the upper bound of summing all the weights included of the cycle. That is the most it can be. Okay?
Wait, so that nearest neighborhood.
It's going to be the up. Yes. Well, I had a shorter one. So if I sum these, I get 119 plus 120 plus 199 plus 150. Can somebody use a calculator and add these up for me? Plus 185.
The most.
That is the most it could be for the possible shortest. So that's the upper bound on the shortest.
No, but didn't we pick the options that were the lower number?
Yeah, yeah. So I'm gonna write down this other one in green. I just looked.
I got 773.
Uh,
Should we?
I'm gonna show you the other algorithm, but I'm pretty sure that's what it. So you got 773? Okay. Can somebody add up the green ones? I believe the green one I actually used the other algorithm, but I'm not sure.
Okay, so the green one is shorter and it visits all the vertices. So would that be the
It's
lower
cheaper.
bound?
Potentially. It might not be the lowest bound.
What?
She's just saying what she's typing in. 722. So that one's definitely less. Part of how I knew it was less was I was like, this is $1 more going on this path than it was going across here, but that's 185 versus that's 133. My path home at the end was cheaper. I don't know for sure. Uh, Does that make sense for the nearest neighbor? Nearest neighbor is pretty easy. No, nothing gives you the answer. I mean, that one, I think the 722 is the some depending on it, you get an upper bound and a lower bound, and it's somewhere in between there. It's not very satisfying. Sorry. Um, so this one says Enrique is planning a trip to Germany. The graph below shows the cities, the distances between them in kilometers. Enrique used the nearest neighbor algorithm to find the upper bound on the shortest trip. It does not say where to start, so choose a vertex. They chose B. Okay. Nearest neighbor to B is A, correct?
Yes.
Yeah.
So 46. Nearest neighbor to A is D plus 50. G is 43. Nearest neighbor to G.
Oh, no.
That's got to be F. 123. I was like, you could go through B to get to F, or you could go through A to get to F, but they're not shorter. And then you got to go back to B 155. Yeah. It's like, remember, you always could go through something else to get there. Doesn't have to be the direct path. Take the shortest path between them. But most of the cases, their shortest path is the direct, or the cheapest path is the direct path, if there is one. The deleted vertex algorithm. Delete one vertex from the graph and all the edges incident. Calculate the length of the minimum spanning tree for the remaining vertices. Create a subgraph by adding the two deleted edges with the lowest weight connected to the deleted vertex to the minimum spanning tree. Okay, so looking at this, they deleted vertex B. It's gone. We're going to then add 46 and 54 to my results at the end. This will be the lowest possible bound. The minimum spanning tree is going from one to all the others. That's the algorithm. Somebody proved it gives you a minimum lower bound. It is not that you will be at least this much. It does not guarantee that there actually is one. That's that low. You get a range. Sorry, guys. So the minimum spanning tree, start at A. Remember, minimum spanning tree is go to the next vertex with the lowest, so 50. Then from D, then you can take the next lowest any way you want, um, which is 43. You could go here from A. You could go AG, but that's more than the 43. And then you just have to get to F. And you could go AF too, but 136 is more than 123. You could go DF. 173 is more. So we just took the lowest. We add those up. We add the two shortest, which was 46 and 54, and the lower bound was 316. It is going to be at least 316 miles or dollars or whatever this is in. Okay. The upper bound is going to be between 316 and 417. Somewhere in there. This is small enough you should be able to test about every possibility to get it. But if you're getting a giant one, well, you've just got some boundaries. That makes sense. On the test, it might ask you to use a specific algorithm. Make sure you write them down in your notes. Yes.